Okay, hi everyone. So this is a big problem. Oftentimes, this is where you're going to use calculus, is for gradients. For example, in machine learning, you'll be doing gradients, gradient descent for neural networks, etc., etc., etc. Okay, so instead of doing A, B, and C, I'm going to start with D. Okay? Part D. Compute the gradient. Okay, that's one thing. And compute the gradient at a point. And compute the derivative at a point for this example. Okay, so first, I'm just going to note the Jacobian. Well, maybe first, the map F has inputs R3 and output, well, there's just one component function, so output is R1. We could just say R. Okay, so then the Jacobian has 3 columns for partial x1, partial x2, partial x3. And so let's look at what they are. I'm going to switch to my formula color now. So partial x1 okay, there's my column. It has one element. What's partial x2? There's my column of the Jacobian. It has one element. My third column, partial x3. There it is. Okay, so that's the Jacobian. Now if I plug in sort of, I guess like this, at p equals 210⁄4, that's what they told me. I called it p and x, I guess, because the variable names were x1, x2, x3. But anyway, well, then I just plug in. Okay, this one is easy to plug in. Now, x1 is 2, so this becomes an 8. And 2 squared is 4. 4 times 3 is 12. 12 divided by 4. Okay, and so now I've done my pre-work. So now, what is the gradient? What is the gradient at a point, and what is the derivative at a point? Well, we're just going to use all this stuff that we computed, all these just partial derivatives. We're going to put them together in different ways. So let me grab words. Gradient. The gradient is a map. In this case, we call it upside down triangle F, or grad F. That's how you say this symbol, grad F. Or I think nabla /nabla will give you this symbol. In Perusall, for example. Now, what is it a map? It's a map from R3 to R3. A good way to think about this is it's a map back to itself. In fact, the gradient will always have the same input and output space dimension. And what does it do? It sends the point x1, x2, x3 to the point 3x1 squared x3, 1 x1 to the third. In other words, it just gives you the one row Jacobian. This Jacobian has 3 columns and 1 row, okay, when we put it together. And so here's that 1 row. And this is a map. It has 3 inputs and 3 outputs. Okay, we just arrange them. Turns out this is incredibly important, and it's called the gradient. The gradient at a point. What about the gradient at a point? So it's a vector. The gradient at a point, grad f at p, I just plug in a point and I get a vector in this output space, R3. So that's easy enough. I'll do the formula. Grad f applied to the point P is just this output. So I already even computed it, 318. It is a vector. How about the derivative at a point? So the derivative of this map that goes from R3 to R, right? So f goes from R3 to R. So what's the derivative of f? The derivative at the point P equals 210 a quarter is a linear map. Okay, so it's a linear map. What is that linear map? It's from the same input space to the same output space as the original map. So now I have to invent new variable names. How about v1, v2, v3 goes to v1 times the first column of the Jacobian plus v2 times the second column of the Jacobian at that point plus v3 times the third column of the Jacobian. And then we just notice that this is actually the dot product of v with the gradient. Just a dot product. Okay, in this case. So this was an example where we had the original map of inputs R3 and outputs R1. The gradient will only make sense when the output is R1. R to the 1, or just R, okay? In machine learning, this will be a loss function or a cost function, etc. In physics, it'll be energy, the energy function, or a temperature function. To every point in space gets a temperature, just one number. Okay. So now I've answered part D. I still have to do part A, B, and C. Okay. So part A, what is the gradient? So I'm going to answer part A right here. So part A, I'll say the gradient of some function like this is a map grad f from Rn back to Rn, from the input space back to the input space. Sending each point to the one row Jacobian. Okay, so that's what the gradient is. Okay, if you want, you can write this out like in a formula. It could send x1, x2 up to xn to what point? Well, the one row Jacobian at that point. So df dx1 at that point P. Let's call this P. So then I don't have to write x. I could have written df dx1 at x1, x2, dot, 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 all the way to xn. That's a lot to write. So instead I'll just say P, df dx2 at P, all the way to df dxn at P. Okay, that's just the first row of the Jacobian. This is the first column. It has one entry. The second column has one entry. the nth column has one entry, and you can view this as a one-row Jacobian. Each column is just one number. Okay, that's the gradient. That's part A. What is the gradient? It's a map. What is the gradient at a point? Well, we just plug into the map. So I'll write B, gradient at a point, usually called grad f at the point P, well, is a vector. It's the output. It's just the output of this map. You just plug in some point and you get numbers here. And so you get a vector. Okay, so like the gradient at a point over here. Here was the gradient, this map. Then the gradient at a point, we just plugged in to these partial derivative Jacobian columns, and we got 3, 1, and 8. So it is a vector. The gradient at a point is a vector. Plug in P to the gradient map. The point here is it's a vector. Okay. Part C. So what is the gradient? It's that map sending a point to its one-row Jacobian. What is the gradient at a point? Just plug in the point and you get an actual vector. That one-row Jacobian just becomes a list of n numbers, like 3, 1, and 8. How is the gradient related to the derivative by a dot product? Because we have a one-row Jacobian, when we take a linear combination of the columns, each column is just a number, and so a linear combination of numbers is just a dot product. And so that's sort of the idea here. How is the gradient related to the derivative? Part C. The derivative and gradient are related by dot product. In particular, in formulas, the derivative of the map f at the point P in direction V is equal to the dot product. Maybe I'll write it like this: the dot product of V with what vector? The gradient at P. That is just V1 times the partial x1 at P plus V2 times the partial x2 of P. This is a number plus dot dot dot. It's just that one-row Jacobian dot product with V will give you a linear combination of the columns. So this is sort of amazing. And has consequences that we will see in the next few weeks. Okay, so part A, the gradient is a map with the same input and output dimension always. It'll just have that the input space of the original map becomes the input and output space of the gradient. The gradient at a point is a vector. It's just the output. When you plug in a point to the gradient map, you get an output, and that output is a vector. Here is the vector 3, 1, 8. Part C, the derivative and gradient are related by a dot product. Very specifically is this formula. Note, everything matters here. df sub p at the point P, if we linearize at P, then we put the gradient at P, we get a vector. V is our input to the linear map of the derivative, and we just take it's a vector, so we dot product these two vectors together, and that gives a number. Okay, this is a number, and that actually makes sense because remember the original map was from Rn to R1, so the derivative at a point should also be from Rn to R1. It is a linear version of this original map. In this case, here's that one number. That one number is a dot product. And here's the example.